What problem does the proposed method aim to solve in the context of learning rate tuning for deep neural networks?
The proposed method aims to solve the problem of classical learning rate tuners undershooting the edge of stability in the context of learning rate tuning for deep neural networks. These classical tuners, such as line search and quadratically greedy methods, tend to lead to ever-increasing sharpness and ever-decreasing learning rates, which can slow down optimization and hinder training progress. The proposed Curvature Dynamics-Aware Tuning (CDAT) method addresses this issue by dynamically driving the learning rate to the edge of stability, where the largest eigenvalue of the Hessian stabilizes. By prioritizing proximity to the edge of stability, CDAT mitigates the progressive sharpening effect commonly observed in deep networks during training. This method aims to exploit curvature stabilization rather than solely focusing on minimizing the loss function, ultimately improving the efficiency and effectiveness of learning rate tuning in deep learning scenarios.
How does the proposed Curvature Dynamics-Aware Tuning CDAT method work? Illustrate step by step.
The proposed Curvature Dynamics-Aware Tuning CDAT method works by dynamically adjusting the learning rate to maintain proximity to the edge of stability (EOS) during training. Firstly, CDAT defines a scaling factor, sigma, which interpolates between a greedy approach, sigma equals 1, and an on-edge approach, sigma equals 2. The on-edge rule positions the optimizer at the EOS, where the largest eigenvalue of the Hessian stabilizes at a critical value for a given learning rate. CDAT dynamically selects the learning rate by seeking the largest value that minimizes a quadratic approximation of the objective, while ensuring the descent direction aligns with the largest eigenvalue's eigenvector. This approach allows CDAT to exploit nonlinear stabilization effects. CDAT incorporates exponential moving averages, EMMA, to smooth estimates of relevant quantities, making it sensitive to information from all eigenvalues of the Hessian matrix. The method prioritizes training at or near the EOS to prevent undershooting, which can lead to a snowball effect of decreasing learning rates and increasing sharpness, ultimately slowing down optimization. By dynamically adjusting the learning rate based on curvature dynamics, CDAT aims to enhance training stability and efficiency in deep neural networks.
What are the theoretical or practical benefits of using the CDAT method compared to classical learning rate tuners?
The theoretical benefits of using the CDAT method compared to classical learning rate tuners lie in its ability to dynamically drive the learning rate to the edge of stability, EOS. CDAT prioritizes training at or near the EOS, which helps in stabilizing the sharpness dynamics during training. By positioning the optimizer on the edge of stability, CDAT mitigates the progressive sharpening effect commonly observed in deep neural networks. This leads to a more stable training process and prevents the snowball effect of ever-increasing sharpness and ever-decreasing learning rates that classical tuners often face. Additionally, CDAT takes into account information from all eigenvalues of the Hessian matrix, making it more sensitive to the curvature dynamics of the optimization landscape. Practically, CDAT outperforms classical learning rate tuners in empirical evaluations, especially in the full batch regime. It can automatically adjust the learning rate to maintain proximity to the EOS, similar to an automatic warm-up schedule. This results in improved performance compared to fine-tuned constant learning rate counterparts. CDAT also offers the flexibility to interpolate between greedy and on-edge rules, allowing for a more nuanced adjustment of the learning rate based on the alignment with eigendirections. Furthermore, the CDAT method can be used in various settings and is not limited to specific optimization scenarios, making it a versatile and effective tool for training deep neural networks.
How were the classical learning rate tuners empirically evaluated in the study?
The classical learning rate tuners were empirically evaluated in the study by comparing their performance against constant learning rate counterparts across several deep learning benchmarks in the full batch regime. The evaluation involved analyzing the curvature dynamics induced by these tuners and observing how they interacted with the edge of stability (EOS) phenomenon. The study found that classical learning rate tuners generally undershot the edge of stability, leading to a snowball effect of increasing sharpness and decreasing learning rates. A theoretical model was proposed to explain these observed failures, highlighting the importance of stabilizing sharpness for successful training. Additionally, a new learning rate tuner called Curvature Dynamics Aware Tuning (CDAT) was introduced, which dynamically drove the learning rate to the EOS. Empirical observations showed that CDAT outperformed fine-tuned constant learning rate counterparts in the full batch regime by mitigating progressive sharpening and automatically adjusting learning rates akin to a warm-up schedule. The evaluation also included proposing a theoretical model to clarify the dynamical mechanisms of CDAT and its benefits in maintaining proximity to the EOS.
What results were achieved with the CDAT method in comparison to fine-tuned constant learning rate counterparts?
The CDAT method outperformed fine-tuned constant learning rate counterparts in a full batch regime. Empirically, the proposed learning rate tuner showed better performance compared to constant learning rate counterparts across several deep learning benchmarks. The analysis of sharpness dynamics induced by CDAT revealed that it mitigated progressive sharpening by increasing learning rates early on before stabilizing, similar to an automatic warm-up schedule. The theoretical model proposed clarified the dynamical mechanisms by which CDAT maintained proximity to the edge of stability, EOS, highlighting the limitations of existing models of curvature dynamics. The design of CDAT focused on exploiting curvature stabilization rather than solely focusing on loss decrease, leading to improved performance in comparison to fine-tuned constant learning rate counterparts.
What are the limitations of the simplified model used to explain the benefits of CDAT in the paper?
The limitations of the simplified model used to explain the benefits of CDAT in the paper include the prediction of runaway sharpening for sigma less than 2 and divergence for sigma greater than 2, which do not align with the stable and useful settings observed in practice. This discrepancy suggests that the model may not fully capture the dynamics of CDAT in real-world scenarios. Additionally, the model neglects the dynamics orthogonal to the largest eigendirection and higher-order terms, which are crucial for stabilizing the edge of stability dynamics observed in CDAT. These omissions indicate that the simplified model may not provide a comprehensive understanding of how CDAT operates in complex optimization settings.